of electrons is the movement of electrons in a small molecule. These two ideas, keep these in mind, that the pictures we are drawing are static pictures and electrons are moving very fast. The static pictures, that's the best we can do, is just drawing a snapshot or a Polaroid in time. How fast are electrons moving? Very, very fast. An electron could move around the Earth, all the way around the Earth in 18 seconds. So when we draw arrows showing an electron moving between two atoms, it's very realistic that an electron could move that very, very short distance because it moves so fast. A molecule, ozone, has a formula of O3. It has 18 electrons in its Lewis dot structure, and it's going to have some resonance structures here. Let's draw a good picture of ozone that has 18 electrons. This picture of ozone here has 18 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It's got 18 electrons, not allowed any more, not allowed any less. Everybody has an octet or an ocho of electrons around it here. An electron is going, now this is a static picture in time of the Lewis dot structure of ozone or O3. Now, electrons are moving very fast. And the reason an electron would move is because it wants to be in a more stable or in a more stable bond or in a more stable position here. This oxygen atom here has 3 lone pairs. And a lone pair is on a lone pair of electrons would like to form a pi bond between these atoms because a pi bond is more stable of an energetic position there. So let's have these lone pair of electrons form a pi bond between these two oxygens here. These negatively charged electrons are now forming a pi bond, a glue between the nuclei or the positively charged nuclei of those two oxygen atoms. This oxygen atom here, if it accepts that pi bond, which it does want more bonds as well, it's going to have 10 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8, and then the new bond, making the total of 10 there. Well, that's really no big deal. It doesn't want 10, so it kicks out one of these lone pairs. It kicks out one of these pi bonds to become a lone pair immediately. And because electrons are moving very fast, this is a very short distance. It's realistic. Let's draw the picture of what that molecule is going to look like once those 2 orange arrows, those 2 movements of electrons have occurred. The position, the oxygen atoms are still going to be bound to each other with sigma bonds because that didn't change. So I always, when I'm drawing my resonance structures, I always start out with the skeleton, like the bare bones of it. This thing started with 3 lone pairs, and one of those lone pairs, so it lost a lone pair. I'm going to draw 2. And it gained a pi bond. So that first orange arrow results in this. Nothing happened to this lone pair. I'm just going to leave that there. This thing lost. This pi bond became a lone pair, and then nothing happened to these guys. So I'm going to put those back on there. So this is a Lewis dot structure. These are 2 Lewis dot structures. They are both static images that are trying to show, and the orange arrows are trying to show the movement of electrons. We have physical proof that this occurs in crystallography images right here, X-ray crystallography. In X-ray crystallography, we freeze the molecules down to a very, very low temperature, and we take X-ray images of the molecules, of the nuclei, and we measure the distances between the nuclei. Now, when we do that, we see that the distance between the nuclei is even for both of these bond distances here. Because that movement is even, or because those nuclei are equal distance from each other, that means that the electrons are moving faster than the X-ray crystallography can image the molecule. If the electrons were not moving, we would see an image. We would see a molecule that had different bond lengths here. But that's not what we see. We see equal bond lengths here. And a way to kind of describe these bond lengths is we could say that this bond right here, 1 or 2, it averages out to about 1.5. We could draw that this way. Saying that like this right here is about a 3/2 of a bond length. Because in our data, in our instruments, we don't see a single bond length. We don't see the single bond. We don't see a double bond. We see an average of these two structures here because electrons are moving faster than we can image them. So these static pictures, these static pictures tell part of the story of the movement of electrons, the resonance of electrons. Thank you.